Okay, so before we start for the JFET amplifier, I try to go over for you a few things, okay? That including the MOSFET we did last week. Okay, so now this is display shows you the JFET P channel. Try to see what the difference between the N channel and the P channel. So basically, the voltage VGG is positive to the gate, and the voltage VDD will be negative. That's only different, okay? And the formula will be the same thing. And for the P channel, ID SS will be same. And channel. But VGS off will be positive voltage. That's only the difference. Anything else, same thing. That means the formula to calculate the current ID still the same. ID SS 1 minus VGS off. Square. Okay, so that they will be the same formula. Only thing is you see the P channel, then the VDD will be negative and the VGG will be positive. That's the difference between N channel. Everything we did for the N channel will be the same for P channel. Only the difference, that's what I bring it up to you. Okay? That's the difference. And also VGS off, they will be positive, not a negative. Okay? So any question about the JFET channel? They can using either N channel or P channel to build the amplifier. However, most popular, they're using N channel. Okay, if not, quickly go through this thing. Okay, so for the MOSFET, E MOSFET operate in the enhancement mode. Okay, schematic telling you that will be N channel and a P channel. N channel require positive gate to the short voltage, and P channel require negative gate, okay, to the short voltage. Equation transfer characteristic differ from that of the JFET and the D MOSFET. Okay, I go back here. Sorry. MOSFET, you get a D MOSFET. Can be operated in two mode, the depletion mode and the enhancement mode. Okay. Depletion enhancement MOSFET that normally they call for that MOSFET. Either positive or negative gate voltage can be applied. For depletion mode, when negative gate to the short voltage applied. Enhancement mode, when the positive gate to the short voltage applied. Generally operate in the depletion. A MOSFET, okay, you can see, recognize the schematic. At least when you're looking into the schematic, you know, you get the MOSFET is MOSFET, okay, N channel or P channel, okay. N channel require positive gate to the short voltage. However, P channel require negative gate to the short voltage. Equation, they will be not like JFET or the D MOSFET. D MOSFET, they will be working like JFET, but not E MOSFET. This is a D MOSFET general transfer. Okay, so this will be N channel and this will be P channel. Exactly the JFET. Okay, JFET VGS off will be negative. However, N channel, P channel, VGS off will be positive. Okay, that one for N channel and another one for the P channel. Okay, this for the Southern D MOSFET. IDSS, they given 10 milliamp, VGS up minus 8 volt. Is it N channel or P channel? Okay, the answer will be N channel. How do we know? The thing is VGS off equal negative. So that will be N channel. If they positive, they will be P channel. Okay, so they say define as a negative VGS off. Therefore, it's an N channel MOSFET. They want to calculate the ID at a VGS equal minus 3. ID equal IDSS 1 minus VGS over VGS off square. Okay, so they calculate, they get 3.991 milliamp. ID VG equal 3 volt. The same formula will be applied. A different right here. This a 3 volt and this a negative 3. So the calculation given you 18.9 milliamp. Any question? The thing on the quiz, you have to do it. And you understand that. Okay, for certain D flip-flop, D MOSFET, IDSS equal 18 milliamp, VGS equal plus 10 volt. And you know that this will be a P channel. The thing is to get positive, VGS off. They want ID at the VGS 4 volt and minus 4. So the formula will be applied same thing. IDSS times 1 minus VGS over VGS of square. Okay, for the positive 4 volt, we're doing calculation, we get 6.48 milliamp. And for minus 4 volt, we get 35.28 milliamp. MOSFET, quite different from JFET and the MOSFET. Okay, they start at the VGSTH. Okay, and that will be telling you voltage for VGS go positive this way. Okay, and on the P channel and the VGS minus VGS go the other way. That's just a transfer. Now, equation for the parabolic transfer characteristic curve of the MOSFET differ from that of the JFET and the DMOSFET because the curve stuck at the VGSTH rather than VGS off on the horizontal axis and never intersect the vertical axis. The equation for the MOSFET transfer characteristic curve is ID equals K times VGS minus VGSTH square. The constant curve depends on the particular MOSFET and can be determined from the data sheet by taking the specified value of ID, they call ID on. That means normally they given you the ID on value. The data sheet in the this figure, we don't care that. They give MOSFET given ID on 500 milliamp minimum at VGS equal 10 volt and VGSTH equal 1 volt. They want to know the drain current for VGS equal 5 volt. The formula, the way to doing calculation, first thing you need to calculate the K. Okay, K from this formula, and you get the K equal VGS minus VGSTH square divide to ID. Now divide to, let's see, K equal ID. That means when the using apply to calculate K, K will be ID on. Okay, and divide VGS minus VGSTH square. Substitute the value, you can get 6.17 milliamp per volt square. Then, now you're using the value of K, you're able to calculate the ID for VGS equal 5. So ID equal K times VGS minus VGSTH square. Okay, so the K we already calculate right here, 6.17 milliamp per volt square times 5 volt, okay, minus 1 volt. VGS is 5 volt and VTH equal 1, okay, and that's why you can get 1998.7 milliamp. Okay, this get the volt square and this get the volt square, they cancel out. And also we given you the related problem. They say a MOSFET given ID on 100 milliamp, VGS 8 volt, and a VGS TH equal 4 volt. They want to find ID when VGS equals 6 volt. That's same thing. First thing you must calculate the K. Okay, K equal ID on. Divide VGS minus VGS TH square. Okay, so you get 6.25 milliamp per volt square. Then you apply it to the formula, calculate the ID. K times VGS minus VGS TH square. You get 25 milliamp. Okay, handling for precaution. Almost device are subject to damage from electrostatic discharge, ESD. That normally you get a job in a company, first thing they training. That means they training for you to how to handling, okay, the circuit board. Most device should be shipped and stored in conductive form. All instrument and metal bench used in assembly or test should be connected to the earth ground. The assemblers or handlers wrist should be connected to the earth ground with the length of Y and a high value series resistor. Never remove and mode device from the circuit while power is on. You are a technician, you have to be careful. Make sure you understand. Okay? That means if the power is still on, you cannot move the circuitry with the Z MOSFET. Do not apply signal while the DC power is off. Okay, that's for handling. Make sure you try to keep reading to try to avoid something you're not supposed to do. Okay, now determine the drain to source voltage. Okay, the MOSFET data sheet given VGS off minus 8 volt, IDSS equal 12 millivolt. Okay, let's see. Since the VGS equals 0, then ID equal IDSS equal 12 milliamp. Okay, that means the VGS equal 0. Therefore, VDS will be equal VDD minus IDSS times RD. Can you follow this example? Why ID equal 12 milliamp? We already understanding the JFET. VGS of equal 0. Then ID will be equal ID SS. Okay? And VDS still the same thing, equal VDD minus IDSS times RD. MOSFET buyer. Determine VGS, VDS for the MOSFET circuit cell. Assume this particular MOSFET has a minimum value ID on 200 milliamp at VGS equal 4 volt and VGS TH equal 2 volt. Okay, so basically this is the voltage divider circuitry. So you know how to calculate the voltage here. Okay, the voltage here will be equal to 24 volt times R2 divide R1 plus R2. That's what they calculate. They get 3.13 volt. To determine VDS, first find K using minimum value of the ID on and to specify the voltage value. That means you have to calculate a K like we already did. ID on divide VGS minus VGS TS square. Okay, then you get the 50 milliamp per volt square here. Finally, you can calculate the VDS equal VDD times ID RD. Okay, VDD 24 volt. Okay, and ID will be 63.8 milliamp. Okay, where to go? We're able to use 63 milliamp here. Times 200. That means the ID 63.8. Maybe we calculate K here. Okay, just a minute. I'm looking at the thing here. Sometimes my iPad display not what I wanted. Okay, so basically we have to calculate the ID. In here we skip calculate the ID. Okay, so you already calculate the K, then you're supposed to calculate the ID. Okay, and if the calculate the ID will be the same formula like we did up here. Okay, where the ID, we just get through here. That's what we need to calculate the ID. ID equal K times VGS minus VGS TS square. Okay, in this example here, ID on, we already calculate the K, and after you calculate the K, we need to calculate the ID. And I believe I skipped that. And the calculate ID will be 63.8 milliamp times RD. That means 200 ohm. Okay? So that is the one we'll be asking you today on the quiz. Okay? Any question on the MOSFET here? No? Okay, so today we will start with the amplifier.
Hi.
Yeah.
On that problem where you missed the ID, okay, I try to work the number. It doesn't seem to come out right.
Okay, let's see. We'll see. You see on the last example, right?
Right. Very last one.
We'll see.
Yeah.
On this example here,
ID is equal to...
you need to calculate the ID.
Right.
Equal K. Right?
Right. Times VGS minus VGS TH.
VGS TH.
And then square.
Square.
So it's equal
to...
Okay,
so K, we already calculated the 50, right?
Right.
50 milliamp per V square. Times VGS.
4.
VGS equal what? 4 volt.
3.13.
3.13.
Okay, now, is it a VGS equal 4 right here?
No, 3.13.
Oh, man. How come they not say it in here? You still see it, right?
Yeah.
Okay.
I used 4. That's why I couldn't come up with the answer.
Okay, now, that's supposed to be at VGS equal 4, right? So let's see, 4.
No, that's the data sheet, Mr. Fan. That 4 is the data sheet number, but the actual bias point in this example is 3.3 volts, not 4 volts.
You mean 3.13?
3.13, yes.
Okay, thank you. Let's see.
Yeah, 3.13, then you get the right.
Okay, thank you.
Okay, I got it.
Okay.
I got a question real quick.
Yeah, just a minute. VGS 2. Okay. That's what you get, 63.8 million. Okay, Mr. Smith.
Yeah, before we were calling that point between R1, where R1 and R2 come together, the VB or whatever, but like a base voltage. Well, why are we calling it V? It's just confusing because when you came up with the VGS equal 3.13, and then you have the other one where you got those 2 red lines at VGS is 4.
Okay, now.
Is that VGS at that point, or is it something else?
Right here.
Right, exactly.
That's it right here. Right?
Right.
So VGS equal voltage right here. The thing is just down, right?
Right.
So 3.13 volts. So
my biggest thing is, my biggest problem is, so we're calling it something different than what we did before.
No, depend.
Joe, you have to read the whole sentence to say value of ID on is equal to 200 milliamp at VGS equal to 4.
Exactly. That's what
at.
That they given from the data sheet.
Okay.
Okay.
All right.
Okay, let's see. Okay, so now we go into the amplifier. That means we have to deal with the DC voltage and the AC voltage. Okay, JFET are commonly used to amplify small AC signal. One reason for using a JFET instead of a bipolar transistor is that the very high impedance of the JFET, okay, J in can be obtained. They want the high impedance input, then they're using the JFET, okay, instead using the bipolar. If you want more gain, then you can using the bipolar, okay? A big disadvantage, however, is that the voltage gain AV obtained with the JFET is much smaller, okay? And JFET can be configuration as following. you get the same common source, CF, common gate, and common drain. Same thing like the bipolar, okay? Bipolar transistor also you can get basically 3 types of the amplifier: common emitter, common collector, and common drain, and common, let's see, common emitter, common
Base.
collector, common base. Okay? Now, if you want to understand more, that normally for engineering level, okay? They say to do the analysis, remember, the 4 steps. First, you have to set on the DC source to 0. That means you converting to the AC circuitry on up the DC voltage will be connected to the route. Okay? And replace them by short circuit equivalent. That only thing telling you. You draw for the AC, then DC source must be shorted to the route. Replace all capacitor by short circuit equivalent. That means you never see any capacitor in the AC module. They be short like the wire. Remove all element bypass by the short circuit equivalent, okay, as introduced by step 1 and step 2, okay, and redraw the network in a more convenient and logical form. Basically, you want to go into detail on the AC circuitry for the JFET or for the bipolar transistor will be following the same way. Okay? First one, they're talking about common source. This is a general picture will be given you. If you're looking on the circuitry, what the type of the JFET they're using to build the amplifier, you understand, you get a different type for the DC. Okay? First thing, there will be a cell bipolar, JFET with a fixed bias. Second one will be cell bias. And the next one will be voltage divider bias. You can using any bias to build the amplifier, no big deal. For this circuitry here, what the bias for the JFET? What the JFET bias will be using for this circuit?
Is it self-bias?
Self-bias.
Exactly, cell bias. The thing is, if the fixed bias, that means you have supposed to get the negative voltage here, right? That will be a fixed bias. And easy to recognize for voltage divider bias. But for this circuitry, will be they using the cell bias. For the cell bias, if you want to calculate on off the DC, like Q point or VGSQ, IDQ, then normally they given you the graphic. However, they don't want using the graphic. That means they have to give you something else that happened in here. they given you VF equal 1 volt. Okay? The main thing is try to calculate the ID. Okay? All of the JFET, ID, and IS will be the same. So if they given you the 4 volt VS, easy to calculate the current flow here, IS. You take 1 volt divide 200 ohm. And let IS also the ID. Okay? And now, when you're looking into the circuitry, you're able to recognize is it the common source amplifier, common drain amplifier, or common gate amplifier. That's the first thing you must be recognized. We're not telling you how to calculate anything inside, but that's the first thing. The second thing, for the source, common source, and the sideway input will be applied to the gate, okay? And the output will be coming out from the drain, okay? And also you can recognize input go up, output going down, okay? Input going down, output going up. I'm telling you the input output will be 180 degrees out of phase. You understand that? Now I will be, I just asking you, what's the name for C here?
Coupling capacity.
Coupling.
AC coupling or DC blocking. That means they allow sideway to pass to the gate, but it's not any DC from here, okay? And now also we can explain to you why we need this resistor here. For the fixed bias, you can connect this one into the negative voltage. If we don't have this resistor here, where you connect the voltage VGS to the ground, they will be killed this sideway here. I think they go to the ground. So that's why we must get the resistor here, okay? So you can able to let the sideway to go to the gate. And what is the name for this capacitor here?
Coupling also.
Right, AC coupling, DC blocking. That means on this side here, you get 2 voltage. One will be VD. That's the bias voltage. And also you get a sideway. So this capacitor here, they try to block that DC bias voltage here. Only the signal sideway will be go to the load. And again, I said the load here like the speaker. And this like your voice, okay? They don't want your voice adding to the DC voltage here to go to the speaker. So that's why the DC will be DC blocking, AC coupling. That capacitor here.
Bypass.
Right, bypass capacitor here. Bypass what? Bypass the resistor 200 ohm. That means in here DC you get a 1 volt, but AC you suppose you get a 0 volt. The thing is current AC go to the source C number 8 here go to the ground. Okay, so that means on the drain you don't have any AC voltage. That's a general picture for you. When you see the circuitry, you're able to recognize what common source, common drain, common gate, okay? And also, what the relation between input and the output. Okay, output voltage and the input will be 180 degrees our phase.
Mr. Pham, I have a question.
Yeah, go ahead.
Regarding C in and RG, those two capacitor and resistor respectively are forming a filter there, a kind of a high pass filter. Can we say that?
Now that's a C in, just a bypass capacitor. Nothing to do with the RS, RG, 1 mega ohm. No relation.
No relationship. So the combination of those two guys there are not filter the signal at all.
Okay, now I'm telling you what the RG. I given you the example for the negative, positive, 2 volt. Okay, so you know, now there will be a fixed wire with the voltage 2 volt connect to the gate. Okay, so now if you don't have a resistance here, then we apply for AC, you must short this power to the ground. Short to the ground. If you don't have a resistor here, this sideway cannot go into the JFET. They will be go to the ground. Okay, that is the reason why they need the RG equal 1 mega ohm here. And nothing to do with the C-in.
Oh, okay.
Mr. Pham,
Excuse me.
Yeah, go ahead.
Isn't it true that really the C and the R actually do have a cutoff frequency, but the assumption is that the frequency of the source is so high that it's well above the cutoff frequency, so that you can treat the capacitor as a short circuit. If the frequency of the source was, say, 10 hertz, then that capacitor would not look like a short circuit.
You're talking about the cutoff frequency?
Right, so this is the assumption here is that the frequency of the source is so far above the cutoff frequency that it's the capacitor is a short circuit. It's not filtering.
No.
Is that correct?
I'm thinking, okay, if you're looking on the gate bias, fixed bias, then you still see a resistor here.
Oh yeah, of course, of course.
Okay, so basically, from my understand, that resistor try to connect to the ground, okay? That basically just for this circuitry, we don't have any DC. And that basically that's just an input impedance for this amplifier. Okay, I don't think anything they deal with the cutoff frequency. Okay, now if you can try, you can run simulation for this circuit. Okay, and try to change RG at a different value. Then you can see the frequency be affected or not. But to me, I can tell you RG equal 1 mega ohm, just an input impedance for the amplifier. Now you
right, so the resistor establishes the DC operating point. But like I'm saying, if the frequency of the source was, say, 10 hertz, and you had a 0.1 microfarad capacitor, the impedance of that capacitor would be 159 kiloohms. So it would not be a short circuit. So you have to have the source frequency high enough so that the capacitor looks like a short circuit. That's all I'm saying. I think that's what we're looking at, but maybe that's
okay. So basically, C in just a bypass or AC coupling, and the value I think inside one handout we already talking to you about a good for the AC coupling. We need to read that back again, okay? Now, AC equivalent circuit. So,
Hey, Mr. Pham,
yeah,
I had a question. I think somebody else might have had one too on that circuit that you just, this circuit here. Did I hear you right? Did you say that there's no voltage at VD? Because at V, from the source, you said that 1 volt is the DC voltage, correct?
we added 1 volt. That's what you say?
Is that what you said?
Okay, we added 1 volt. They given.
Okay, and then you said that the AC signal would go around the resistor and go to ground, correct?
Yeah, AC can be bypassed by the capacitor.
Okay, I got that part. Now, what did you say the voltage of VD was? VD, from drain to ground.
That's just 1 minute. Hello? Okay, at the D, right?
Right, correct.
You get 2 voltage. One the DC bias. Is that right?
Okay, yeah. So you do get a DC bias from there to ground, and you also get an AC voltage, correct?
Get 2 voltage.
1 AC, 1 DC.
Perfect.
Okay, thank you. You answered my question. Thank you.
However, when they go to the output, they don't want any DC. So that's why you get C out bypass.
Okay, got you.
If you are designer, okay, engineer designer, then you need to know what is the value for the capacitor supposed to be for the good bias, for the good coupling. I think on the handout, maybe bipolar transistor. We already talking about that.
Okay, thank you very much.
No problem. AC equivalent. Now they converting to the AC. So basically you can see the source right here and connect to resistor 1 mega ohm. If you see right here, you not see any capacitor. Okay? The thing is capacitor like the wire. Okay, like the wire here. Okay, that's one side. The other side, that means from the drain, you get the current ID going. ID equal GM times VGS. And also on the other side, on this side here, first thing VDD have to be round. Okay, they have to be rounded here. When you convert it into AC. So the rounded here and the capacitor here will be shorted, okay? And now you can see, you can get a this resistor and this resistor here, the load, connect to the drain and both go to the round. So they will be in parallel, okay? Now, when you deal with the amplifier, and we need to deal with the input impedance and the output impedance. Input impedance means your source here. When you're looking into the amplifier, that's what they call a G in. And this is the output, when you're looking from output into the amplifier, that's what they call GR, input output. And this is a module, okay? And we cannot change anything. So GL, some book they say RL, RL. L means the load. R small r will be AC load. Okay, this is the AC load, or you can say GL, same thing, doesn't matter. Only thing you understand, you're looking from the output to the amplifier, how much resistance you see. That's what they call output resistance. On the input side, RG equals G in, which is 1 mega ohm. That means this is the input resistance to the amplifier. This occurs because with the practically zero gate current, the gate source resistance designated RGS approximately infinity, AC equivalent. Now, they try to repeat that thing and they got try to give you a little more formula. You understand it? This handout I take from one of the university, okay? They take for their students. Now, something, before I can do it, I can ask you one thing. Okay, you get a 1K. 1K. What the total equivalent?
0.5.
Equivalent you already learned. 1K times 1K divide by 2, right?
Yes.
That means 0.5. Okay. Okay. Now I can get one. 100K. What equivalent?
About 1K.
Almost 1K, right?
Yes.
That means you take a 1 times 100 divide 1 plus 100. Correct? That will be telling you what? Okay. Now this resistor here, RD. RD, that means the internal resistance of the JFET. You can see they given you the set area right here. What that means? This part here will be inside the JFET. Okay? So if you're looking into that more simple than the bipolar, G in, you're looking this way. And you can see they get the equal RG, 1 mega ohm. And the G out, okay, equal big D. Now, if you get the resistor outside, they will be that will be output impedance. They not count for the value here, R small d. The reason is R small d will be bigger than output resistance. And they gave it to you the gain equal V out divided to V in, and that will be equal minus GMRD. Now that will be given to you the circuitry, okay? They get also R big D. That means the drain current, the drain resistance outside. That's a load resistance, okay? Or RD just a a drain resistance RD. Okay. Then now, let's see, phase relation, a common source amplifier configuration at 180 degree phase shift between input and the output. Okay, for me, at least at this time, can you doing a calculation for me in this circuit? I want VGS Q, IDQ.
It's fixed bias.
Okay, I'm not doing calculation, so I don't know which one is the right answer. Who get the answer for me?
Minus 2 volts.
Minus 2 volt. The thing is VGS off equal VGS minus VG minus VS. VS equal 0. VG equal minus 2 volt. Okay, so VGS equal minus 2 volt. And if you want to calculate the ID, IDSS 1 minus VGS over VGS off. Square. So what you get ID?
Mr. Fan, I have a basic question here.
We're talking about the basic equation.
Oh, I have a basic question.
Uh-huh.
You said BS is equal to 0, and that is because it's, the source is connected to ground, right?
Right, that's a circuit.
Okay, thank you.
7.66.
Okay, one gets 7.66 milliamp.
I got 5.6.
Oh man, 7.66, and another one get 5.
0.6.
5.72.
5.6 approximately. So I've got VGS over VGS off is equal to 2 over 8, which is 1/4, which is 0.25. So 1 minus 0.25 is 0.75. 0.75 squared is 0.56 times 10 milliamps is 5.6.
But VGS
Mr. Pham, it says the pinch off is equal to -8. So that means VGS off is +8, correct? Because you said the pinch off and the VGS off have the same number but different sign.
That's a mistake in the slide.
Okay, so that's better.
That's the thing on the handout to get that confusing.
Yeah.
I took it as a positive.
So now if I'm doing, then I say 2 divided 8.25 square times 10, 5.625. And VD will be equal VDD ID times RD. So what VD equal? The thing I want to get the right answer, so the people couldn't follow it. Later on, they do it. They know the right value. They able to get the right. What VD?
RD.
VDD means 20.
8.75.
Equal that.
ID will be 5.625 times 2.
Like that 8.8.
I got 8.75.
Yes, 8.75.
Okay, 8.75. Thank you. Okay, now calculate the GM0. Is it a 2 times IDSS, right? Divide, I believe, VGS. Is it VGS or VGS off? Maybe VGS off.
It's off. Yeah, because that's the anchor point for the curve.
2.5.
So GM0, who get it?
2.5. I got 2.5.
2.5 M, right? M Simon or what?
It's milli.
Siemens. Siemens.
Siemens.
I think it's I think it's millisieverns, right? Because the IDSS is in millisieverns.
Let's see. The unit will be Simon, right? I forgot that.
No, it's because IDSS is in milliamps. So it's milliamps divided by volts. So the answer is, as you showed, 2.5 millisiemens.
So you get the 2.5 MS or what?
Yeah.
Okay.
Yeah.
And if you calculate the GM formula, we already know the formula. Now GM equal GM0 times 1 minus VGF over VGF off, but not square.
I got 1.875.
Okay, one get 1.875 million.
Me too.
Right?
Yeah, agreed.
If you guys get the same or you get a different, please let us know. We want to get the correct answer.
I got 1.875, the same thing they got.
So good. So they wanted to gain. Okay. AV equal. You want it, you have to look up here. AV equal minus DM times RD. Big D. So they will be minus 1.875 times RD 2K 2000. Oh, so what AV you get?
Anybody get 3.75 or?
No,
Yes.
3.75.
Minus though.
Minus 3.75. That's what I got.
Thank you.
Times 1,000.
What do you mean times 1,000?
Because you got ohm instead of
That's
kilo.
what I said, times 2,000. RD right here.
Yeah, I know that. But when you multiply it 3,750.
Then the GMs in millis.
Oh. Yeah, I got it. I make mistake.
Okay.
Yeah.
And they want input impedance. G in, we already know.
Hey, Mr. Pham, just real quick, does that make sense that you have a minus gain?
Yeah. That's telling you input output out
Out of phase?
But when you get a minus.
Mr. Pham, you should put 2 instead of 2,000 because that one is milli.
Thank you. I forgot that.
Okay.
The thing is, this is a milli.
Yeah, that's milli.
Okay, thank you.
Okay.
2K. Input impedance mean 1 mega ohm here. G in 1 mega ohm. And output impedance, G out. In this case, they will be equal to 2K. Okay, so basically, we all given on up the calculation for that circuitry. I don't want you to understand too much anything. If you're able to do it, that is good. But the minimum requirement, when you see this circuitry, you're able to do your calculation, okay? And normally they will be given to you the formula. You don't have to memorize.
Hey, Mr. Pham.
Yes, sir.
Real quickly, on your last answer for Z out, I'm just saying if you had a resistor at the end of C2, you would short out that
they will be parallel.
Right, they would be parallel with the 2K.
Right.
Okay.
But you have a no load.
Right. In this case.
Right, thank you to bring it up for them. Otherwise, the other people, they hit into the almost the same problem, just a minor difference.
Right.
And they can be wrong.
Although sometimes the load is never included in the output impedance calculation, because if the load is included in the output impedance computation, well, then what's the actual load? You're going to deliver power or voltage to something, right? So it depends on it's kind of a choice whether you include the load resistor as part of the output impedance.
Yeah, that's what is that Richard? Yeah, that's what that's what I'm saying, Richard. I was just saying, what if he had a load there, then you would short that out, and then it would be in parallel with the 2K, and then whatever.
Personally, I wouldn't do it that way. I would say the load is separate. That's what you're delivering power to. So I'd calculate the output impedance based on the drain resistance and the internal drain resistance of the FET, and then I'd calculate the power transfer to the load based on that output impedance. But that's just a personal.
Yeah, I was just doing it the way the model that Mr. Pham has been given in the past.
That's just a normal.
You have to do it the way that's going to give you the right answer on the test. That's
see the different Mr. Richard here, master degree EE. So he knows too many ways.
Richard, you're way ahead of us, man.
But you know, you just learn my way.
Yeah, like I said, I'm just here to help if I can, just provide maybe a slightly different point of view. But you know, the answer is the answer that gets you the correct test result.
Hey, thanks a lot. I appreciate that. Thanks a lot.
I have a question, Mr. Pham.
Go ahead.
So basically, in this circuit, the gain is determined by minus GM times RD. It is very clear to me what is RD, but it is not very clear what minus GM represent on this circuit, which portion of the circuit. I can follow the equations, I can replace the numbers, but basically, what does represent the minus GM in this circuit?
Minus, that means the difference. Opposite. Okay, now you can see right here. Okay, so basically, this is the display for the circuit without the load, like the one we just did. Okay, and now the voltage here, that means V out, right? Okay, so the V out will be measured from here to the route, right?
Yep.
Across here, okay?
Yep.
And basically, you can see you get the current flowing here. The value will be GM times VGS. VGS, that means voltage from here to here. That's the VGS, okay? And that will be, let's see, we don't care on that one, okay? The thing is too big resistance parallel with the big D. So that's why they ignore that in the calculation, okay? And let's see, and the GM, what you calculate for the GM? GM, you calculate, you get is it a minus? Right here. Okay, so minus GM times with RD. That's why you get a negative voltage. And if you're looking into here, you go into the calculation. So the VL will be GM times VGS, and let's see.
But that's a minus GM right there, right?
Yeah, we already get the GM is a negative, okay? And let's see, I get a gen, then I will be go into the basically the calculate the V out. V out equal the current flow here times the RB, and the current here GM VGS. Sometimes I memorize what I already know, but now I forget it.
Yeah, but if I understand well, GM is in Siemens, right? So the unit is Siemens, so is conductance, right?
Yeah.
So it's talking about one property of the component itself, how easy the current flow through that component, right?
GM.
Actually, it's a transfer function. It's a ratio of an output current to an input voltage.
Okay,
so
okay,
it's
but
not, so it's not a physical conductance. It's a transfer function with the dimensions of conductance.
Oh, okay, but that dimension of conductance is associated to some properties of this component itself.
Exactly.
Okay, okay, got it.
Okay, thank you, Richard. Okay, let's see. Now will be 6:39. Okay, so you think 10 minutes you can get through this example here. Otherwise, we have to get the test for today, the quiz. I given you 10 minutes.
Hey, Mr. Pham, can you go back to that other one that you were, that last, yeah, right there. Thank you.
The thing is, I want to calculate clear for all of the problem here. The people not here today, or the people cannot quite understand, they can look back into the video and they can say recording or not the calculation. That I just want to tell you that students want to learn, okay? If you don't, who cares? I don't care either. Okay, VGS. Now, same thing. You see that? The same problem. They given you VGS. The thing of that will be a cell, okay, bias. Then they given you 1 volt. Easy to calculate the ID, okay? And VGS, we can see, let's see, basically, VGS off we already get, IDSS we already got, okay? So what VGS equal?
Well, I know your ID has got to be 5 milliamps.
Right.
ID, for
ID has got to be 5 milliamps because you got 1 volt from source to ground, and you said that IS and ID is the same thing. So if you take the reciprocal of 200, you get 5 milliamps.
Okay, 1 volt. Divide 200.
200. And you get 5 milliamps.
Okay, you calculate, you get 5 milliamps.
Did anybody else get that?
Yes, it's good. Yeah.
What VGS equal?
VG minus VS.
Okay, VG minus VS.
Minus 1.
VG,
Minus 0.8.
come on.
Minus 1. You get a minus 1.
Minus 1 volt.
So IDQ equal to IDSS times 1 minus VGS over VGS.
If you want to calculate ID and take a VS over RS.
ID equals IS, so you don't need the formula.
You say ID equal IS, correct? All the time, ID, IS will be the same for the JFET. Okay, then GM0. ID at a 2 times, right? ID at over VGS up.
Mr. Pham,
Yes.
for IDQ, why are we not using IDSS times 1 minus VGS over VGS off square?
Now, can you say again?
Okay, for IDQ,
Okay, you say IDQ.
okay, is equal to,
Well, ID at that.
right,
Okay, time 1.
minus,
VGS up. And square. Okay, so you can using this one. Okay, when you get the VGS, you substitute into here.
Right. Since we got VGSQ already,
Yeah.
we substitute
But
in.
the thing is they must given you VS, correct?
Right, they give you VS14.
Either way, okay? If they don't give you VS voltage, then you have to calculate substitute in VGS here also include the ID. So you get an ID on both sides of the equation. So that's a very, very hard to solving that equation. So they try to get away.
But if you use that formula, you get 5.625, which in the previous example is exactly what we did.
Yeah, but the thing is that's a minor difference, okay? They're supposed to be identical.
Hey, Mr. Pham, I think I see what he's saying. If you use that equation right there and you put crunch the numbers, you'll get 5.625 milliamps. But then on the source is 1 volt. So if you take the source and that 1 volt and divide it by 200, you just get 5. So there's a difference between a little bit of difference between 5 milliamps and 5.625 milliamps.
Okay.
The difference I think comes about because the 1 volt specified in the problem is not quite accurate.
Okay, there we go. There we go, okay. Richard.
The actual source voltage would be a little bit different. But since it's given in the problem, you have to solve the problem using the source voltage of 1 volt and the source current, which is identical to the drain.
So, Richard, while you answering that question, so are you saying that the formula is more correct than the 1 volt that's given?
Yeah, but if you weren't given VGS, you'd have to solve it graphically, right? Or do
good night, man. Good night. Yeah.
Yeah, so it's a hard problem to solve, as Mr. Pham said. You have to either solve it graphically with data or solve a system of algebraic equations, which is really difficult.
Okay.
Yeah.
I was thinking the other thing is, since one way you're given 5 milliamps and the other way you're given 5.6 milliamps, maybe add them together, divide by 2, and use the average.
I believe, you can using the formula, IDSS times 1 minus, okay, VGS, VGS of square. That will be more, the accurate than the other way.
Okay, thank you.
However, normally you have to understand when they're telling you to measure at a certain point, I say they want measure V at 1 volt. You cannot get identical, exactly 1 volt. They have to give to you upper limit, right? The tolerance.
Right. Right.
So that's why, you can do either way. They still okay. And now you can calculate your GM0, GM, voltage gain, and the other thing will be input impedance, output impedance, okay? And also the V out. So we will be continue on Wednesday. Now I have to stop here, okay? And make sure everyone download your report for the quiz today.
Thank you.
You're welcome. Okay, make sure download that report for the quiz.
What is that, number 14 or something?
Yeah, 14.
You need to share the screen, Mr. Pham.
Oh, all the time. Thank you. Thank you.
No problem.
You got to do the specs in the clock too.
US means MS, yeah?
Yeah.
Okay.
9, 10. Square.
You know your number 11 is cut off at the bottom, right?
Yeah. I can see the display, maybe you not.
Yeah, I can see it just fine.
Okay.
Mine's okay.
So
I can see it.
you have to check your computer system.
Expand your window a little bit, Joe.
Look like this time the timer ran okay.
It works good today.
When you get a test, I given you 2 hours, so I can get a free for 2.
You don't get free time, Mr. Pham.
Okay, that's it.
Good night.
Good night. Upload your quiz.
Okay, look like Miss Kumi got a request for you to go over quiz number 12 and 13.
Next time, not today. Tomorrow, please.
Why do not get Zoom to me?
Yeah.
Anytime.
Thank you.
I will help you out.
Thank you.
Okay, so we'll see you guys Wednesday.
Thank you, Mr. Pham.
Thank you.
Well, good.
Thank you, sir. Thank you.
You're welcome.
Thank you.
I'd like to say thank you to Rita. He did very good job in our program.
Nighty, night, night.
Thank you.